Well, good morning, everyone. Wonderful to see so many both familiar faces and new faces, so I hope to get the chance to speak to all of you over the next couple of days. I'm going to give a talk really to introduce a sort of new idea into this space. So I'm going to leave most of the implications for cooperative AI to those discussions that I hope to have with you. So if you leave this talk thinking, well, what has this got to do with cooperative AI? I claim that is by design. So I'm going to talk about AI squared towards AI capable of AI science. I want to start by playing you a little video of something that happened just over 9 years ago, which I think you'll recognize.
And this is what Thore from the Google team was talking about. Is this kind of evaluation value?
That's a very surprising move.
I thought it was a mistake.
Of course, this is the famous move 37 in the AlphaGo Lee Sedol challenge match. And I'm going to use this as an example of an innovation. So it was an innovation for two big reasons. One, the move itself was in some sense previously unknown, and it was previously unknown whether it was a good or a bad move. But in fact, it wasn't a very surprising move in one sense, because if I'd been playing Go, I can't play Go at all, I think I'd have about a 1 in 330 chance of making this move. And that's a pretty good odds of making the move of the century, right? But of course, it was then falsified, i.e. it was known to be good by collection of evidence, by playing the game, and then by future analysis. And indeed, it and AlphaGo more generally altered the theory of what moves are known to be good. So here is a nice study from a couple of years ago about the effect of superhuman AI on human decision-making in Go, citing this increase in novelty of the human play now that these better moves are known. So all this is to say that AlphaGo came up with this innovation. It was a novelty, but it's not just a novelty. And so a couple of years ago in the SAFE retreat, I talked a little bit about what innovation was in terms of this thing called the knowledge matrix, and this talk is going to be really a development of that. So the knowledge matrix you could think of as the matrix which says, given an agent A, what are the things that A knows? Well, these are the assumptions, like I think you've got a pretty good idea if I remove the top block from that Jenga tower, what would happen, i.e. it would stay standing. If I removed one of those middle blocks from the Jenga tower, where there's only one block in the line of 3, the Jenga tower would fall over. There are things that A knows that A doesn't know. So these are gaps, for example. So I know that I don't know the temperature at a given altitude on Jupiter, but at least in principle, I could know that information. There are things that A doesn't know that A knows. So this one's probably the hardest one to get your head around. But you can think of this as tacit knowledge, or things that you can figure out by reasoning. So I know, I don't know that I know the solution to this Sudoku. But if I sat down with the Sudoku, I know the rules of Sudoku. I'm not dreadful at Sudoku. I could know that. So it's something that I don't know that I do know, or at least could know. And then there's the most exciting bit, things that we don't know, and these are the discoveries. So innovation, then I claim, is the process of going from the bottom right to the top left, i.e. from discoveries to assumptions. It's the process of making discoveries. In other words, going from unknown unknowns into known knowns, and hopefully now you see how this fits with the first slide I had on AlphaGo. So how does AlphaGo do this? Let's say we had the quest to automate innovation. I'll come back to why we might want to do that. Well, it starts in some sense with the theory of Go. That's the policy or value network. And then using MCTS, it goes from this theory of Go, things that in some sense it doesn't know that it knows, and it turns these into things that it knows that it doesn't know, i.e. a policy, a conjecture about what moves are going to help it to win the game. Then it does self-play. So it tests that conjecture with experiments playing against itself. And then the data of the games is analyzed and evaluated and turned into training data for the policy and value net. So this evaluation piece is pretty trivial. It's just, did you win the game or not? But more generally, as you'll see, this might not be trivial. And then there's a process of reinforcement learning to build the theory of Go. So putting all of that together, you might start to think that this reminds you of something, this process. No one's going to be brave. The scientific method, exactly. The other thing it might remind you of is the infinity symbol, which is quite cute if we're talking about automating innovation. When I joined DeepMind, which was just over 8 years ago, I was pretty excited because I thought, well, all we need to do is take AlphaGo and we'll generalize it to everything, and then we're kind of done with the AGI problem. It turns out that's quite difficult. Why? Because the rules of the game of Go put a very strong constraint on the space of theories, and the reward function places a very strong constraint on the space of conjectures. And what we really want to see is not just innovation in Go, but the kind of innovation that characterizes human technological development, which also co-occurs for very, very deep reasons with increasing cooperation among humans. So one of the biggest challenges then is how can you not only do this scientific method in a single domain, but also go to more general domains. So if you imagine this knowledge matrix extended now over a third dimension, where that dimension in some sense is more generality. And at least if you believe David Deutsch, he thinks that the sort of function of a scientific theory is what gives you this reach. It's got, you may come up with a theory in one domain, but then it can allow you to make conjectures about things in different domains, and therefore expand your space of knowledge. So the question is, how can we express the scientific method as a domain general open-ended algorithm? And so I think what's changed in the last couple of years about this question is we've really got a recipe to do it, which is that there are now foundation models. So to borrow from Jeff Clune, he said AI sees further by standing on the shoulders of giant human data sets. So how does this pertain to the question of automating innovation? Well, you can think of language models as domain general mutation operators. So you take a prompt, you think of this as the parents, and then the output is the children, and these are mutations of the prompt. And lots of people in this room have worked on this. I had some work with Aaron Wallander on this at the start of the year, where we used this as a mechanism for measuring the open-ended cooperation of language models by having language models, in some sense, mutate the behavior that they would have in a game. In a cooperation game. We got some very interesting results, which you should go and ask Aaron about in terms of the relative cooperation of the models. Also, language models are domain general selection operators. I like Jenny Zhang's summary of this. We can use foundation models as models of interestingness, because in some sense, they've already internalized human concepts of interestingness from training on vast amounts of human-generated data. Okay, so how does that answer my question of how can we express the scientific method as a domain general open-ended algorithm? Well, we can just follow a recipe that Karl Popper expressed very clearly in 1959. His theory of science says we're choosing theories which hold their own in competition with other theories. In other words, science is this process of natural selection over theories, where the theory which is the fittest to survive is the one that's testable in the most rigorous way. And so now it's maybe obvious to you what I'm going to do. I'm just going to say, well, we can use language models as the mutation and selection operators, and we use theories as the substrate in this evolutionary process. So a language model can propose a theory based on existing theoretical and empirical knowledge, and then a language model can write code to subject the theory to empirical testing and falsification. You can write an evolutionary procedure for AI research. And perhaps most excitingly, and potentially most dangerously as well, we need to think very carefully about this, is that this Popperian AI can be recursively applied to improve language models themselves. So I'm going to flash up some very quick slides about what's been going on in the last year in this space. There's been a huge amount of progress. So we know language models can express theories in experiments, and there's been 2 works from Sakana AI that have shown great progress here. AI scientist papers have started being accepted at workshops, and just a month ago at the ACL conference as well. These are papers in some sense fully generated by AI, all the experiments and all the text. Language models can accumulate innovations, and just in the last month we've seen AlphaEvolve generating things like new matrix multiplication algorithms, improving on algorithms from as much as 50 years ago. And again, I think this was three weeks ago, there's a fully self-referential, self-improving system, again, from Jeff Klein's lab and some folks at Sakana. So we've got this proliferation now of these benchmarks for AI squared, and the question is sort of how can we do this in a responsible and safe way? And I'm going to finish with just a comment on safety, which slightly connects it to cooperative AI, and you can ask me more about this afterwards. So I said, this automated innovation, we want to kind of go through some safe process of cultural evolution in order to arrive at that. And why do I believe this is a safe process to go through? Well, in some sense, cultural evolution is the only superintelligence generating process that we know can be safe. We produce children, and we don't seem to be too worried about that. And they do tend to be more intelligent than us, at least if you believe the Flynn effect. I think we all agree in this room, the first AGIs are unlikely to be individuals. They're likely to be collections of systems that interact with the cultural evolution of society. So, making progress on understanding this innovative process that's changing society is really important to understand the impacts of AGI more generally. And so I think it's almost a necessity. And the final argument I quite like is this idea that, in fact, it's getting harder to do science. And if we are going to make progress on solving hard things like cooperative AI, we actually need to leverage AI to solve these big scientific questions. So I'd love to talk more about that later in the day. Thanks.